Hi, ladies and gentlemen. I'm Yu-Wei from Cybersecurity Technology Center of National Taiwan University. Today I'm talking about our paper entitled An Efficient Dynamic Rule Placement for Distributed Firewall in SDN. Here's our outline. First, I will give a brief introduction of what is a distributed firewall and how to manage this distributed firewall in an SDN environment. And secondly, I will give a rough introduction about why it is important and what is the challenge of rule placement in this SDN distributed firewall. And in the following section, I will introduce our proposed algorithm, and I will integer linear programming formulation to do these rule placement. And as a result of our formulation, this integer linear programming suffers from an NP-complete problem. That is, if this problem gets bigger, which maybe the number of rules or the complexity of the topology grows larger, then this rule placement problem can become undesirable, time-consuming. As a result, we have proposed this resource constraint splitting in order to address the high computation time of solving this integer linear programming problem. And last but not least, I will show our experimental result for this resource constraint splitting algorithm and how does our network perform at this rule placement. So first, by introducing the architecture of a distributed firewall and SDN supported switches, all the network devices now can become a firewall in an intranet. As shown in the right figure, now you can see that not only the gateway switch can filter anomaly packages, but also these switches in the intranet can detect attacks from hackers. This raises a new challenge, which is how to properly place firewall rules inside your intranet. And management this rule placement in this distributed firewall is an error-prone task. And several previous studies has done on this rule placement in SDNs, such as Daifan or Nguyen Yan. They have worked on the rule placement of routing and endpoint policies. And other works has also proposed a similar integer linear programming based solution on rule placement. Upon rule updates, most of the proposed algorithm will have to recompute the rule placement, and this causes additional computation costs. So our work have addressed the high computation cost of integer linear programming based solution and proposed this resource constraint splitting in order to lower the computation time. And this resource constraint splitting can also tackle the challenge of dynamic updates of firewall rules. As the network environment becomes more complex, there's more need and more frequently that the firewall rules will need to be updated. And usually these updates will not influence other old firewall rules. As a result, resource constraint splitting can let you minimize your time taken to recompute the rule placement. Also, this study conducts experiment in an emulated internet environment, mainnet, to compare the performance with that of the previous studies. Okay, and this is our proposed algorithm. In our integer linear programming formulation, we have a decision variable, that is v I k, and this is a binary variable that indicates whether a rule Ri is placed on a switch Sk. Vik is equals to 1 if and only if Ri is placed on Sk. And there are also two constraints, rule protection constraint and T-can limit constraint. And here's a figure to illustrate it. What is the path? What is the path? For a firewall rule like this, it filters, it allows the package of protocol SMTP to mail server, from mail server to internet. And this firewall rule has defined paths inside an intranet, for example, as shown on the right, with router 1, WAN 1, gateway 2, gateway 1, and router 1, WAN 2, gateway 2, gateway 1, and router 1, WAN 1, gateway 3, router 1, WAN 2, gateway 3, etc. So the path defined by a firewall rule is that from the source to all the possible paths that from the source that the package will pass through from the source to the destination. Okay, so here comes two constraints. The first constraint is rule protection constraint. This constraint defines that for all paths, and this path is defined in the previous slides, it is a list of SDN devices, and it's a set of paths determined by a firewall rule, and the summation of rule placement must be greater than 1. And what this means is that the rule must be placed somewhere along the paths, and this path is all the possible paths that the package might go through. As a result, this constraint will enforce that all the package matched by this firewall rule will be enforced by the matched package, will be enforced on the matched package. And secondly, for every SDN devices, TCAN memory is a precious resource, and we'll have to limit the TCAN memory, and we will have to limit the rule placement on each SDN devices. And this is the meaning of TCAN limit constraint. Well, we have this objective function that minimizes the wasted bandwidth and memory consumption. The wasted bandwidth is the bandwidth that induced by the placement of firewall rule. Let me give you an example. If the firewall rule is placed further upstream on the path, then the matched package will be dropped or filtered earlier. As a result, it can save some of the intranet bandwidth. So this is the meaning of wasted bandwidth. And memory consumption is quite straightforward. It is that the rule placed on all SDN devices. And however, this formulation of rule placement is NP complete. So we have proposed to use resource constraint splitting to split this integer linear programming problem into multiple small problems. Well, the first step is that we can use protocol source IP, source port, or destination IP, or destination port actions, or any arbitrary combination of these fields to divide firewall rules. With the optimization goal mentioned above, the rules are placed near the ingress SDN devices determined by the source IP, since it can minimize the wasted bandwidth. And most of the firewall rules have the source IP of the internet, that they are filtering network package from the internet. So we have used the same source IP to group the firewall rules. And this method of dividing rules makes the integer linear programming separable, and the placement of various subset of firewall rules is formulated as several small ILP problems. And the second step, we will use a TCAM memory assignment. Since that the TCAM memory of each SDN devices is shared among all the small integer linear programming problem, so that the original integer linear programming, the TCAM limit of the original integer programming problem is splitted in two. Each small integer linear program, according to mainly the breadth search, and this is because that for each small ILP problem, these rules will be placed further upstream, that is near the source IP. And the principle of our division of the ILP problem is that we use different source IP to split the firewall rules. As a result, this breadth search will assign these TCAM memories according to the breadth. Okay, and the last step is that we will split the original large ILP problem into multiple ILPs, and these ILPs are splitted according to their different source IPs. Okay. In the following section, I will explain what our experience. We conduct experiments on the computation time for solving an ILP and multiple ILPs by using this resource constraint splitting for dynamic update. We also perform network simulations with realistic network topology and compare the network performance in terms of latency and throughput with all other studies and rule distribution in SDN. And on the right, this shows a specific network topology we use. We use network topology from the Internet Topology Zoo, and this is the BT Asia Pacific Network topology. Okay. So the complexity involved in rule distribution is dominated by two factors: the numbers of firewall rules and switches. Here we tested different computation time with the growing number of rules. On the left column, we can see that the original ILP problem will cause an exponential time, especially when the number of rules grows to 40,000. And for our resource constraint splitting, and the computation time is a bit more steady growth. And also, we have conducted an experiment to compare the computation time to solve an ILP versus the number of switches. And this shows the similar trend. that the computation time of complete ILP is exponentially growth, and the computation time of our resource constraint splitting is more linear. Also, we have compared the computation time with previous study. And we can see that on the leftmost column, the computation time of Zhang, they also shows more exponential growth since that they use an integer linear programming formulation. However, Chen, they have used a somewhat more heuristic way to do the rule placement. And our RCS, resource constraint splitting, can maintain similar computation time with that of trains. Last but not least, I will show some of the network performance compared with these two previous work. So we have compared two network performance. First is throughput and the second is latency. We can see that the throughput inside our network topology after rule placement is more resistant to the growing number of firewall rules, which is green, shown in this figure. And as the number of rules grows, the other two work have a significantly lower throughput. Also, for the latency, well, Zhang's rule has more similar latency with us, but it increased when the number of rules increases to 25,000. To sum up, we presented the RCS algorithm that can provide the same solution for ILP-based rule placement problem. We reduced computation time in order to deal with dynamic update of firewall rules. Our distributed firewall showed better performance than those of several previous studies in terms of higher throughput and lower latency. In the future, weights can be added to different factors in the objective function. Also, different schemes for gauging firewall rules can be exposed. Okay, thanks for your time and attention. And the following page is our reference in this presentation. Okay, thanks.